will not be pure. It will have some impurity. Anyway, so now both these, of course, silicon as well as the impurity, how it is going to work. Okay, so in this particular chapter, we are going to see the semiconductor fundamentals. Probably you have already read this part in your first year physics or ZEE, wherever, somewhere, 12th somewhere. So moreover, this particular topic will be a revision of that. However, it will brush up the concepts, and these are the things which will be used in the next chapter, where we will be exactly, actually we will be learning about how a solar cell works. Okay. So let us start. So of course, through this particular chapter, I'm going to go a bit fast. Fine, because this is mere revision. You know almost every concept, you know. Only I will discuss something which is moreover related to solar cell, where these a particular characteristics or particular parameter might be important, and of course we will discuss it at the time when we discuss solar cell, but I will emphasize that part only. So let us start with the carriers and energy. Obviously, the carrier for us electrical is electron. Okay, that is what, because that is responsible for conduction. So positively charged nucleus, and then there will be negatively charged electrons. They will be revolving around like solar system. That is what the Bohr's model is. Okay, and moreover, it's a roughly correct model. It never happens. Okay, electron is not moving, or even the electron. When we say that current is flowing, there is no electron which is flowing. It's the energy which passed from one atom to another. It's not that actual flow. However, what is most important for you is the charge of electron. So obviously it has got a negative charge, 1.6 into 10 raised to minus 19 coulomb. These values are standard values, and I will never give these values in the question paper. So you should know these values. Fine. Anyway, we'll be using it very frequently, so automatically it will you will by heart it. Okay. So obviously, number of electrons in an atom, that is what crucial, and that is what recognizes the element. So element is recognized by the atomic number. So motion of this charge, again a classical definition, motion of this charge, that is mostly electron, we will call it as the flow of current. However, later we will learn that both electron as well as holes are responsible for the flow of current in semiconductors. So the Bohr model says that electron that will be orbiting around the nucleus, and it will have some momentum because it is moving. But the thing is, it will have only discrete momentums, and that is given by this P, which is equal to mvr or nh pi. That is this h is the reduced Planck constant, h by 2 pi. And obviously, it depends on mass, velocity, and the radius in which it is orbiting. Now, obviously, mass is constant. The velocity will be also constant. But however, what it will change will be, velocity would be constant if they are in the same environment. So what is changing is the radius, and later we will see that this radius depends on a simple integer constant n. And that's why we can have, as it is an integer, we can have 1, 2, 3. So obviously P will be in number in that multiples of 1, 2, 3, and that's why we call it as discrete. Angular momentum is not really will be important, but rather energy would be very interesting to note. And the point is discrete. So I will talk about more about this discretization when we talk about the energy band. Yeah. So Bohr basically proposed the hydrogen atom. So this, if there is an electron in the hydrogen atom which is orbiting the proton, then it will have a stable radius. So that's why hydrogen has got 1 in the outer radius. Its atomic number is 1. But then electron, it is revolving. So obviously there should have been some balance, because electron is not moving out or in towards the proton. That's why we compare this with the solar system, like solar and sun and earth. So there are two forces. One is electronic attraction, that is between the electron and proton because of their opposite polarity, and there will be a centrifugal force that must be balancing each other so that the electron so-called can revolve around the atom. Anyway, so now this red eye, what I was talking about, you can see the formula. This particular formula you might have derived it in physics. We will not do that derivation, but from here onwards, I mean, this would be something we will be using. This radius directly will be using, and there is one formula for energy. That is what we are going to use directly, and because we don't want to reinvent the wheel, so what we'll do is we'll use this for any expression that we'll be deriving in this or the next chapter. So you can see here the radius which we are talking about, all everything is constant, right? Epsilon naught or Q or this M, everything is constant. Only change or only variable thing can be N. Okay, so obviously that's why as N changes, the radius is going to change and the energy is going to change, and that's why we always get all these discrete parameters. However, later we learn that when we have got too many atoms, so for us, even a small amount of silicon, if we take, it is virtually infinite. So when it goes from few atoms to infinite atoms, the what you call it as the discretization reduces. So lesser the number of atoms, the discretization will happen. We'll see the diagrams a bit later. Anyway, so this model, in this model, you have seen that as the radius of this orbit increases, then the energy requirement will be decreasing, right? In the sense, uh, if n is larger, then the radius is quite larger, and the energy requirement for removing that electron will be now very less. So for any orbit, this energy, as I've said, it will be potential energy plus the kinetic energy. So that attraction between the proton, and obviously because of as it is in moment, it is due to the motion. So you can note down this particular formula. So energy is now equal to the values given, and as I've said, everything is constant except n. So if you substitute all the values of the constant, what you are going to get is En is proportional to 13.6 by n square. So as n increases, the energy decreases. However, there is a negative sign for that, and that's why you will find out that if the radius is smaller, then the electron is very near to the proton, and that's why removing that would be a very energy intensive process. However, if the electron is quite at the outer radius, outer orbit, then the energy would be relatively low compared to the innermost orbit. So I hope you have written this particular formula, and also you can write down this one just to note down. Whenever I show some formula, better you write it down automatically. Okay. Fine. So we'll be solving some numericals. So at that time, all these formulas you will be requiring. Fine. So now this is what exactly I mean. So when you represent a hydrogen atom, or in general, what you say, any element, you can see that in 1, 2, 3, 4 in integer it will increase, and the energy actually is going to decrease. Now the point is that why there is a negative sign, it means that suppose at n equal to 4, if I have to remove the electron somewhere sitting over here, I have to impart only 0.85 electron volt of energy. However, if it is at n equal to 1, I have to give 13.6. So this is exponentially increasing because of the square term. And obviously the energy difference will go larger. The point is, you can see here I'm drawing these red eyes, different red eyes, because we have this model. Okay. However, when we are drawing the schematic, we don't like to draw these circles, right? So that's why we draw horizontal lines. So this line is a representation of whatever the orbit we are talking of. And even I'll show you sometime that the energy, so these are the energy levels, but in fact these energy levels are not circular, not even linear or something like that. It will be quite something wacky in nature. Okay, so something like this. And this is the valence band and conduction band. Anyway, we'll come back to come to that later. But you can see conduction band minimum and valency band maximum, and this is called as the band gap. So I will give you some examples a bit later. So remember that the point is energy levels. These are the schematic diagrams what we are drawing. These are not necessarily the actual energy band diagram if you calculate it. Okay, this is for representational purpose. So some quantum mechanics comes into here. We will not do it too much because for our course quantum mechanics is not required. However, one can form wave equation for these atoms, and one can find out that for solution to exist, we have to define certain possible energy levels for the atom. So based on that, we can define 4 quantum numbers. You already very well know the first 2 ones. The principal, that is n. So this is the describes the energy level within an atom. That what we call it as shells. So obviously it will have integer values n equal to 1, 2, 3, and so on, as we have discussed. So it will have 2 n square electrons. So it will have 2, then 8, and then so on. And then next is the momentum, because every what you say electron is moving. This second number partly tells about the different momentums which are available. So there will be some different subshells, and these subshells are called as SPDF. Okay, so this 2 is fine, but this 8 is, you are going to break it. Okay, so it will be broken further into the momentum levels. So these are the subshells. For every n, every energy level, there will be subshells, or for every shells there will be subshell. Then next is the magnetic number. Now for every L there will be this two or more, but it will be in pair, a different number of magnetic numbers given by n, and the last number will be spin. So electron can have only 2 kinds of spin. So either it is positive or negative, or you can say clockwise or anti-clockwise. So this is because by the principle, that pigeonhole principle, at a particular position only you can have 1 electron which is having a particular spin, either positive or negative. Anyway, so these 4 numbers can be used precisely to define the position of an electron. We use it rarely, just in a what you say go. I'm telling you. So let us talk about silicon, and let us apply all this. So obviously we get we have this silicon atomic number 14. So this has to be distributed. So obviously 2, 8. So for first 2 levels will get filled, and then the remaining will be filled in the third one. So this can be split into 2, 8, and 6. So now you can apply those quantum numbers. So you have n1, 2, and 3. So first 2 are absolutely filled, and then at the third one, you can see third one there are what you say 6 are remaining. It doesn't fulfills the third level. So we can have subshells. Obviously subshells will be here as well, but I'm not showing. So SP, that is what can go for 2 and 4. So it will fill up the 6. So you have, so these 2 will have n equal to 0. Then the other things will have n equal to 1. So 2 plus 8, 10. Oh, sorry. What I did? Yeah. So 2, 4, 6. Sorry, 2, 8, 4. So 2 plus 8, 10, 10 plus 4, 14. Okay, so this last one will have only a 4 one. So you can put this into various orbits, and you can split this into two 6 and then 2 6 and onwards. Anyway, so that is not so much important for us, these quantum numbers. Anyway, so point is, what we have to understand is the energy will be what is say quantized, and it depends on what is the energy level at which it is sitting, which is moreover defined by the number of n. So as you increase this radius, suppose let us say there is hypothetically one electron is at every level, so you can see that there will be, if there are 5 6 electrons hypothetically in every level, we'll have these levels, and these are absolutely discretized. So uh, every electron has got a different level. So uh, it means that they are discrete and you can pinpoint it. Okay, so there is no band. There is a very precise level of one electron which is taking one energy. Anyway, so what happens is, obviously the electrons, whenever the surrounding changes, whenever the energy input output changes, let us say there is one level which is higher energy level and other one which is lower energy level. In simple principle, every electron will try to sit at the lowest energy whatever is possible. However, due to some reason, it may happen that it, it can go up, and once that energy is withdrawn, it can come down. So this particular two processes, the emission, so electron can go from higher energy to lower energy, so this we can call it as emission, and the other one can be absorption. So here the electron is absorbing the energy, it goes to the higher energy, and then when it releases that energy, it goes back down. So this emission and absorption are the vital process for any semiconductor to work, whatever might be the devices, diode, or what you call LED or whatever. Okay, so this energy, how they are going to change, depends on few factors which we have already discussed, which is defined by their number. So n, l, m, and then your spin. So these four quantum numbers, whatever we have seen, will decide what will be the energy whatever is required. So if you are talking of any two levels, you can take the difference of that, and that is what the energy either should be absorbed or should be emitted to change the levels. So now obviously when we talk of quantum dots, there are very few atoms we are talking about. But when we talk about the bulk material, bulk means even 1 centimeter square is a bulk material because it has got virtually infinite atoms. So when we are talking of such a infinite electrons, and again when we know that Pauli exclusion principle, that every electron can have its unique energy levels, then something different starts happening when we are bringing more atoms together. In a sense, we are bringing more electrons together. So now not only that electron is what is interacting with the proton of the nucleus of that particular atom, but it is also interacting with the other atoms and other electrons. So when you are bringing these so many atoms together, what happens is you have to have more and more energy levels so that you can satisfy the exclusion principles, or you can satisfy the energy occupancy level. So when you have so many of atoms in this crystal, what happens is, of course this is a schematic, so you can see that the distance or the energy levels are so close that after these infinite atoms, it is very difficult to distinguish between them. So moreover, it feels like that they are now linear instead of the discrete levels. So that is what we say, that for the bulk material, it is as good as they are forming a band over here, and that's why we call these diagrams as energy band gap. So that band word comes because of such a what you call it as closely almost touching each other kind of and making a linear thing. However, you can see it here, it is discrete. You can literally count, and you can differentiate them. So bulk material will be always have non-discretized or a band structure. So this is the poly exclusion principle, that you have to split those energy levels. So when we have got the standard levels, so 1, 2, 3, and then SPDF and whatnot, so everything will be split. And so this level is a discrete level, but when you have got multiple electrons, this is what will happen, and this is called as the splitting of energy levels. And you can see that this is entirely a band of electrons which are trying to occupy that particular level. So that's why, depending upon what is the lattice spacing, and depending upon what you say, what levels we are talking about, we will have different levels. And that's why when we define the band gap, it is the minimum gap between the conduction and the valence bond, because it is not linear, as we saw. As I've told, it will be something like this, wacky, and then we have to find out this is the minimum in conduction and this is the maximum in the valence bond. So this becomes the band gap over here. So that is what the discretization and the energy level splitting. So there are, of course, we are talking about semiconductors, so we have got some elemental semiconductors. Obviously, the valency is for silicon, as it is 284, the valency is now 4. It means that neither it has got electron to use, or it doesn't have just one electron it can accept to complete the outermost orbit. So silicon is 14. And again, you know that these particular columns will have similar properties. So silicon, like silicon, carbon can also be used as semiconductor, and germanium can also be used as semiconductor. Germanium silicons are quite well known. However, carbon is now recently being introduced. However, you know that carbon is a semiconductor, and that's why you use it. But carbon has got different properties. For example, a graphite, it is soft, however it can conduct. So that's why you use it in machines for what you call yeah, brush. Okay, you can use brush, but then you can so these are called as elemental. I mean, only one element is useful for making a semiconductor. However, you can combine this 3 5 or 2 6, you can combine, and you can form kind of alloys. So we have about 4 types: elemental is silicon and germanium. Compound becomes when you are going for 2, like gallium arsenide. Then we have a ternary and quaternary. So all these are possible semiconductors which can be used. Gallium arsenide is most famous perhaps after the silicon, because gallium arsenide, actually it's very costly. However, the efficiency of gallium arsenide solar cells is quite high, about 35 to 40%. So when solar cell actually started, it started with gallium arsenide, and it was a thin film technology, so it was very expensive. That's why gallium arsenide cell never could make up into the revolution. Only when silicon was discovered that it could be used for solar cell, then only really the telltale application took place. So gallium arsenide, although the cost is high, but still efficiency is also high. So definitely it was a better choice for what is a space application, because in space application money is not that important. However, the weight of the panels itself is very important, and then you want to produce more energy, obviously, in a small space, at small what you say payload, you can say. That's why this gallium arsenide was preferred for space application, and still it is preferred. But the problem there is one more problem as arsenic. Arsenic is bad. It's a toxic element, and obviously the process creates the problem. And then again, the same case is with the sulfur, cadmium. These are heavy metals, and heavy metals always create a problem for earth. So that's why it is normally avoided. Anyway, so let us talk about this silicon and in general semiconductor structure. So in silicon, obviously, when the atoms are together, they are going to form a bond. And as I've said, as it is 284, you can neither lose or gain electron. So the only option remains is sharing of the four electrons so that you can make the bond. And this bond is obviously the covalent bond due to the sharing. So here you can see if there is one silicon, four from one and four from other will be together, and that's why every now element, every silicon atom is with that surrounded by 8 atoms, 4+4 configurations. So this conduction is in a simple sense. So whenever they
Sir,
are,
you
they
are
are
not.
not free. Hello,
Sir, you are not audible.
my network is fine. Hello.
So you're not like no, 4 or 5 seconds ago.
Yeah. Okay, okay. It is a bad network quality. Just wait. Just now it gave the signal that you poor quality. Yeah. Am I audible now?
Yes, sir.
Okay, just give me a minute. I will, switch off some of the net eating. Let's say, just give me a minute. I'll close some applications. Yeah. Is sharing available now? Hello.
Yes, sir.
And I'm audible as well, right?
Yes, sir.
Okay, fine. So my point was these electrons have formed covalent bond. So they are already engaged. Okay, they are not free. So what happens is there is nobody to conduct the current or what you call it as there is nobody to move around, and that is how we have defined the current. Movement of a charge constitutes the current. Now the point is, when we say that they cannot move, we are defining it at the absolute zero temperature, because it means that they do not have energy of its own, so that they break the bond and become available. So that's why they cannot participate in current flow or absorption or whatever. But obviously, whenever you give the energy in some form, it may be the heat. Okay, so here let us say we are talking about the zero temperature. Now, if I increase this temperature to, let us say, room temperature of 300 Kelvin, it means that I am giving some energy to that, and that energy is sufficient for some of the electrons to break the bonds, and then they become free to move about the lattice, and these free carriers now is able to move the able to conduct and able to constitute the current. However, that is what, in general, conduction happens. But whenever, as I've said, we require a source. In this case, I was talking about the increase of the temperature. But in solar cells, what can happen is the energy is coming because of the photon, which is coming from the sun. So at room temperature, at elevated temperature, anything above zero, there will be some electrons, and at room temperature there will be enough electrons so that you can have the conduction. So obviously, when your temperature is quite low compared to room temperature, the semiconductor is going to behave as an insulator. But when you increase the temperature, or give it some energy, it will constitute the current, so it becomes the conductor. So that's why we call it as semiconductor. So depending upon what is the situation, it will work either as an insulator or as a conductor. Now, what happens when this electron is moved? Okay, so obviously it is breaking the bond, so that bond is absent. So electron is now available. So when electron moves away from its place, then there is some void which is present, or there is some space which is left behind. And obviously we have removed negative electron from there. So there has to be compensation for that charge. So what happens is, in whatever that broken bond, a positive space is created, and that is what we call it as a hole. So you have to remember that electron is a real quantity, is a real thing. However, hole is a fictitious quantity. So whenever there is absence of electron, we call it as call it as hole. So obviously the hole is positively charged, and then it automatically should be understand that these two will be always in pair, and that's why we will be calling it as EHP, obviously, which stands for electron hole pair. So wherever a hole is created, obviously electron should be moved out. Okay, so that's why this will always occur in pair, and the equilibrium will be always maintained. So later in solar cell, we will understand that we have to create these electron hole pairs, and we have to make some arrangement such that electron conducts and hole conducts. And you can easily imagine that why I want a special arrangement, because if electron and holes are again combined somehow, if it is combined, then we are losing EHP, point number one. And if they combines, then obviously we do not have any carrier, so that it will help in conduction. So our point is that create electron hole pairs, make it sustained, uh, make them participate in the current, and once it has participated, finish the race or whatever, then you can combine them. So they should not combine before taking part into the conduction. So these are the important points which we should remember for solar cell applications. So for solar cell application, band gap is important to us. We'll talk about that band gap. Then number of free carriers, how many electrons and holes are available for conduction. So we should produce more and more EHPs, and we should make sure that these EHPs are sustained. It means that they live longer, or in a technical sense, they have got a higher lifetime. So the first process is generation, where we create EHPs, and then there will be recombination, that is combining or annihilation of the electron and holes. And this recombination should not happen before it takes part in the conduction. Otherwise it will be wastage. Whatever we are generating, it will simply become wastage. So whenever we talk about engineering, this is what we have to take care of, that you should have higher generation, and you should have a very less recombination, so that more and more number of free carriers will be up. And obviously these free carriers will be dependent on band gap, and band gap is a property of material. And that's why, even though you talk of any electronics, your FET, SCR, whatever you take, it basically depends on, first thing is the material, and second thing, it depends on the engineering, that how we are managing the functioning of the device, how we are optimizing it, and how we are reducing the phenomena which are bad for us. Okay, so remember these points. So from here onwards, I mean, at least in the solar cell chapter, this is what I'll be always referring to. Okay, our ultimate goal will be always to work around these three things as well. These three things only, as far as the electronics and conduction and other things are concerned. So let us start talking about the first one, which is band gap. So there are two bands, as I have already told. One is conduction band, so where electron has now enough energy, what we call it as free, and he is free to conduct. That's why it is called as free. So normally this is the higher energy state, and it can be denoted, that energy can be denoted by EC. C stands for conduction. Then we have got valence band. Now here the electron was earlier bound, but sorry, it has gained some energy to move to higher energy side. So suppose there is some electron, it moves up, then the electron is here, then obviously a hole has to be created here. Anyway, so this is a lower energy state. We call it as EV. Now, of course, as I've said, there are certain specific energy levels which are available for in an atom. So the electron has to move from here to here only. It's not his wish that okay, fine, I will rest it here, somewhere here. No. Okay. Uh, so in pure silicon, let us say if it is the band gap is 1.1 electron volt. By the way, we can define the band gap as the distance. Distance means the energy level difference between the EC and EV. So it has got 1.1 electron volt. So for this generation to happen, we have to give, let us say, a photon of 1.1 electron volt so that the electron will go up. Okay, so if there is a, let us say, a photon of zero point 0.5 electron volt, it cannot knock out the electron and it cannot send it to the conduction band. So it means that photon is a wastage. So this is the reason, and this is why where we talk about the spectrum utilization, if you require silicon cells must have all the photons with 1.1 electron volt, but solar spectrum has got everything from very low energy to high energy, and that's why whatever is below 1.1 gets wastage. Anyway, so there cannot be a mid level, and here I am talking about the what you call pure silicon. Later we will learn about the impurity. So when impurities come, there might be a chance that something is sitting in between, and then electron can go and sit here. However, as it has not gone to the other side, this is useless for us, and that's why we should avoid the impurity. Anyway, we'll talk about that later. So this number and energy of these free electrons, whatever the participating in conduction, is the basis of operation of any electronic devices, as I've said. So that's why the band gap is important. That's why the material is important, because for a material, under normal circumstances, it will be unique band gap. For example, silicon 1.1 electron volt. And why I'm saying unique circumstances? Because as we have seen in nanotechnology, for the same silicon, I can show a band gap of 2 electron volts. It is 2.2 electron volts up to. So this is possible. But at nano levels, we are talking about now the normal physics of semiconductors. So both electron and hole can participate in conduction once you generate, as I've said, now you have got electron here and then the hole is created over here. So both, as both take part in the conduction, combinedly I can call it as carriers. It can be negative or positive, doesn't matter, because both are going to conduct. So electron and hole both can be carriers. So for operation of these semiconductors, both are going to play the role, and obviously either we give electrical signal or optical signal, we can perturb them, and we can transfer electron from valence to conduction, or we can, in a simple sense, we can create EHPs electrically or optically. Optically means you are shining the light. Electrically means what you're doing in diode, you are giving some positive voltage, positive negative, or in a sense you are biasing that diode. So it means you are giving electrical energy. Obviously when you are hitting it, it will also work, but the problem is heating energy would be too high to substantially gain electrons in the higher energy state. So that's why we always draw the energy band diagram to explain the things. However, you should understand that only the valence and electron bands are EC and EV. These are the only two which are drawn, because that is what defines the whole what you say conduction. We are not worried, as I've said, we are not worried about any other bands. What we want is this one only. That is the band gap, and that is what the minimum and maximum difference between the minimum and maximum energy levels. Okay, that is what we are concerned about, so that we can demonstrate how the things are working. So whenever we draw band diagram, y-axis will be all obviously energy, and x-axis is the distance. It is the distance from the top. Okay, so energy, the distance from the top, and obviously we require some reference, and that reference will be always vacuum. So can you guess what will be the energy of the vacuum? Yeah, can you quickly guess what will be the energy of the vacuum?
Zero.
No. Shivam Tripathi, can you guess the energy of the vacuum? Interestingly, I am his BTech supervisor, Shivam Tripathi. I hope he is still registered. Okay, so do you remember our formula for the energy? Do you remember the expression minus 13.6 divided by
By
n
n
square,
square.
correct? Ha,
Yes.
ha. So what is that? This vacuum means what? You are going absolutely away from what you say the your lower state, right? So and what do you mean by vacuum? You remove everything, you suck out everything, correct? So there is no electron which is left. So now tell me how much energy it will require to remove each and every electron. So that will be 13.6. So obviously that's why it is far. Anyway, with respect to that vacuum level, we are defining this EC, EV, and any other energy that what we require. So there is always a reference over here. Anyway, so now as we have defined band gap, let us try to look at metal, non-metal, and the semiconductor, how exactly they differ. So, as I've said, band gap determines the conducting properties, and it is unique to a particular material we are talking about. Metals, we know that they are good in the conductors of electricity. So you can see that the conduction and valence band, they are overlapping each other. Okay, it means what? Even without giving any additional energy, still I have got some electrons which are in the conduction band. So that's why you have ready-made already readily available electrons for conduction. But when it comes to insulator, these two bands are absolutely far away from each other. So for example, diamond is an insulator which has electron band gap of 5 eV. So it's a very large 5, although it looks like very small number, but it has got electron volt multiplied by that. So that's why it's a huge energy. And that's why you will see that even when we try to thermally excite this insulator, is you require a huge energy for that. And that's why even insulator after heating doesn't becomes conductive. That's why insulator we that is a good thing about the insulator. Otherwise, in electrical application, after heating, the insulator will become conductor, so it will become a problem, right? So this is the reason. Now, at least to the batch, I think illumination, that batch. Okay, we had some discussion last time for the power system design laboratory. Do you remember? I asked one question regarding glass. Anybody remembers? Anybody remember the question regarding glass? Aishwarya Roy, I think you were in that batch.
So, no, sir, I don't remember the
You
question.
don't remember? Who were in your batch? So
My batch, sir.
you batch means not your group. I mean, there were some 25 people for which lucky people, those who learned something about illumination from me.
So, me and the rest of the dual degree electrical.
Dual degree. Good.
Yes.
Dipankar Jena. Dipankar
Yes,
Jena.
sir.
हाँ सर
Yes,
कुछ
sir.
याद आ रहा है? हाँ?
No, sir. I don't remember.
No, you don't remember. Okay, good. Uh, Nikhil. Nikhil,
Yes, sir. Sorry, sir, I also don't remember.
you don't remember. Who remembers them? What's the point in them learning? Should I withdraw your grades? Snehashish Samal.
Yes, sir. No.
Do you remember or not?
No, sir, don't remember.
Good, good. Aman Verma,
Yes, sir.
what? Yes. Do you remember? I'm not taking
No,
attendance.
sir.
Do you remember? No. What?
No, sir.
What? No, sir. And what? Yes, sir.
Sir, the question regarding the glass.
What? You remember or don't remember?
I don't remember, sir.
Good, good. Uh, Thumukunta Vidya, right? 4103. Yes. Vidya, absent. Good. Niharika Dalai.
No, sir, I don't remember.
And Swagatika Dalpati.
Sorry, sir, I can't recall.
You can't recall. Okay, fantastic. So nobody recalls. Good, good. So anyway, the question was why the glass is transparent. Anyway, so if you don't remember, then obviously you don't remember the answer as well. I think I gave that answer. So anyway, my question is now still open. Why the glass is transparent? Question is open to everyone. Why the glass is transparent? Glass is a solid, right? I mean, now let us not
I
go into
guess it does
technical.
not absorb any energy,
Any energy means what?
like visual spectrum.
So my point is, when you look outside, you don't feel glass. I mean, glass is like
But the band
like
gap is very high.
band gap is very high. So what happens?
The electron means light passes through it.
So practically, but practically, what happens? I mean, you get 100% light on the other side.
No, no, sir.
So what you call that that property of glass? What is that property of glass? Transparency. Do you get 100% transparent glass?
Translucent.
Translucent नहीं भाई, transparency, transparent. Okay. So do you get 100% transparent glass?
No, sir. Some
So
of
the
it
photons
got
aren't
No, sir.
absorbed by the glass.
Tarun Kanti. Yes, Tarun Kanti. Amartya. Vaibhav. Vaibhav.
Yes, sir.
हाँ
Sir,
बोलिए.
transparency.
आप क्या सो रहे थे क्या?
No, sir.
हाँ, तो what I asked something different.
Sir, property of glass by which we can see through the glass.
Sir.
Why we can see through the glass?
नहीं भाई, आप सो रहे थे. Anyway, हाँ, somebody is trying to say something. बोलिए.
When the light falls on the glass, since the band gap is very high, so the electrons which get excited, they don't give out the when they are going back, like they are emitting light. So that is not
Emitting
in the
light,
band.
so glass emits light.
No. The electrons
No. Please
during
don't
emission.
please don't go down that line. That's wrong. Okay. Anyway, so my point is, glass is not 100% transparent because the point is, of course, it will have some other elements which are very impurities. What we call it in a simple sense, they are impurities. So that's why some of the light will get absorbed in the glass, and normally you get 10% what is a 10% absorption, so 90% and all that. And that's why whenever some good glasses, you can see the difference. You have been to mall, right? So there will be have you ever purchased glass, drinking water glass?
Yes, sir.
Yeah, so you will find out that there will be one glass which is 10 rupee, 20 rupee. Have you checked that? Cutting chai, anybody has had this cutting chai typically in Mumbai? You remember that
Yes, sir.
glass?
Yes, sir. Yes, sir.
Yeah, yeah. Okay,
Yes,
compare
sir. It's
that
too hard
glass
and thick.
with hard and thick. No, we are not in glass technology. We are in semiconductor. So what I'm trying to say is that glass is very cheap glass. And then you have got yeah, even your spectacles, right? So those glasses will cost around 1,000 rupees or something. Forget the lens part of that, but you will find out that these glasses are too transparent. Okay, so why don't you use that chai wala glass for your spectacles, because of such a property. Now, do you also remember that there is something called as UV protection on your spectacles, right? There is some layer of UV protection.
Yes, sir.
Yeah, what is the function of that?
It reflected the ultraviolet rays.
It reflects ultraviolet, and there is something another property as well. Polarization. Polarization. Is it there? Now, by the way, have you? Of course, you must be knowing there are certain glasses which turns black when you go out in the sun. Have you seen that?
Photochromic, sir.
Yes, sir.
Yes,
Yeah,
sir.
photochromic. Yes. So as soon as the light strikes, they changes their band gap. Okay. So the point is this: everything plays related to band gap, and it relates to the quality of glass relates to how many impurities are there. So for silicon, it has got band gap of 1.1, 1.2 electron volts. So you can, if you calculate the energy at 300 Kelvin, that is at room temperature, it has got a 2.59 milli electron volt. Do you remember this number from somewhere? Do you remember this number, 2.59? Oh, sorry, 25.9. Sorry. 25.9 milli electron volt. Have you came across this number in your diode or electronics somewhere? First year electronics or second year electronics? Because you cannot move, without this number. Because when you calculate the energy of electron at 300 Kelvin, this is what you are going to get. So you must have encountered this number multiple times. Anyway. So the point is, you can understand how much energy we should provide such that the semiconductor will start conducting, and as that band gap is higher, we get insulators, and in metal it is overlapping. Now, in the first what is a topic, I told you that there is a difference between solar thermal and solar PV. Although both of them has got the same fuel, that is the solar energy. However, they are absolutely different as far as the operation is concerned. So you can see that the solar thermal uses, which material it will use out of these three? Hello, which material it will use out of these three? I've shown it's a continuous band gap, so it is a metal. Okay. So anyway, so they uses copper tubes. Normally, copper is a material, but they are painted black. Again, why black? Because they want to absorb every energy, every photon that is being incident on that. So here light to heat conversion is done. So whenever some energy falls on that, more electrons comes for conduction, and they heat up the material, and that heat is then transferred to the water which is flowing through the copper tubes, and then obviously your water gets heated. However, when it comes to solar PV, then the things are different, because now you already have some difference in this. So whenever a photon light falls, the electron here will jump over here, EHP is created, and now here we have to engineer such that we should keep them separate. They should conduct somehow, and then through some external load, and then the current is once the current is established, then you can combine them so that the it works. So this separation of these two, electron and holes, that is what we call it as a photovoltage conversion, light to photovoltage conversion. And that's why The first, there are three steps in solar cell working. First step is the separation. Then, sorry, first one is the generation. Then we have got separation, and then we have got the recombination. Okay, so this is how the in three steps we generate, or the solar cell works. So this is the importance of this. What you call it as the use of insulators. So just by, if you have got a different material, your engineering is different, and then only the solar cell is possible. You can never create a solar cell with copper material. Okay, of course, how exactly this engineering is done, we will learn it in the next chapter. Anyway, today we will stop here, and we'll talk in detail about these properties in our next class. Okay, so I think that's all for today. Thank you very much.